Okay, so again, we're still working through this circuit. We have a collection of resistors, and two are in series with each other, two are in parallel with each other. We've constructed an equivalent resistor, so this one resistor is in some sense equivalent to the original four. Equivalent means if we connect it to a battery, point A and point C connected to the terminals of a battery, the same current will be pulled from the battery. The same current will flow through the battery. Not the same current that flows through these two resistors here, because the current I splits into these two smaller currents, but the total current, I1 and I2, which will be equal to I, that will be the same current which will be drawn from the battery if instead of connecting these four resistors in that configuration to the battery, we connected that single resistor of 14 ohms. Okay, so we've done the calculation for the equivalent resistance, 14 ohms. Then we connect it to a battery with a 42 volt potential difference across it. So therefore 42 volts between points A and C. How much current is going to be in each resistor? This is the problem that we want to solve. Okay, so as I said, we work backwards with these three equivalent circuits. This last one is the easiest one. So it's easy to imagine that if we hook a battery up across this resistor, well, we know how to calculate the current, because the potential difference of the battery will be equal to the potential difference across the resistor between A and C. So, and we know that V is equal to I times R, or in other words, I is equal to V, or delta V, divided by R. So what's the delta V? It's the 42 volts. What's the R? Well, it's the final equivalent resistance, which was 14 ohms. I know it says R sub series here. It's series just because in this very last step of the calculation for equivalent resistance, we had two equivalent resistors that were clearly in series. That's why we summed them to get 14 ohms. Okay, so this is the equivalent resistance, 14 ohms. So the current which is pulled from the battery is 3 amps, 42 divided by 14. Okay, so that means the current I is the current, let's see, if we go backwards here, so if that amount of current, what was it again, 3 amps, goes between A and C, well, in this intermediate equivalent circuit, that will be the same current that flows through this 12 ohm equivalent resistor and this 2 ohm equivalent resistor. 3 amps flows through both of them. Okay, go back to the original diagram here. Well, whatever the current is that goes through this equivalent resistor, it's the same current that flows through each of these two that were in series with each other. So 3 amps goes through the 14. Therefore, 3 amps goes through the 12 ohm equivalent resistor. Therefore, 3 amps goes through these two resistors, the real resistors in the real circuit. Okay, if you follow the logic there, hopefully it makes sense. Now, on the other side, it's a little bit more complicated. Okay, because I know that I is equal to 3 amps, but I don't know how the 3 amps divides into I1 and I2. Okay, now what I do know is that the total is 3 amps. I also know that these two resistors were in parallel with each other because they have the same potential difference. And whatever the potential difference is between B and C in this original diagram is going to be the same as the potential difference between B and C in this middle diagram. Okay, we're going to use that fact. Okay, So between point A and B, if you refer back, if you have your notes in front of you while you're listening to this screencast, if you look between A and B, okay, so what's A and B? It's between this point and this point, okay? Well, in the middle diagram, that's the convenient one to use, the potential difference across it is, well, the resistance is 12, the current is 3 amps, so the potential difference between A and B is 36 volts. And we know that the total potential difference is 42 volts across everything, okay? So that means what we've just shown is 36 volts between A and B, and well, we know that there's 42 all the way from A to C. So if I take the difference between those two potential differences, that should tell me the potential difference between B and C. Okay, kind of maybe a little hard to follow if you're just listening, but try to write it down and hopefully it'll make sense. So the potential difference between B and C is the difference between those two potential differences, 42 minus 36. So that means there's going to be a 6 volt drop between points B and C. Okay, 6 volt drop. If there's a 6 volt drop, think about what that means. Between B and C, a 6 volt drop. Oh, that's just the voltage potential difference across each of these two resistors. If I know the delta V across each of these resistors, the 6 ohm resistor and across the 3 ohm resistor, it's the same value, whatever, I think it was 6 volts. And I know the resistance, then I can easily calculate the current that flows through each one just by going back to really the V equals IR equation. Solving for I, it's I is V divided by R. So for the 6 ohm resistor, it's 6 volts divided by 6 ohms, so that's 1 amp. And the other one you could calculate in the same way, same potential difference, 6 volts divided by the resistance, and you would get the current. But another way to think of it is I2 is just the total current that comes into that branch point, at point B, right? Subtracted minus the current which flows through branch 1, cross resistor 1. Okay, so 3 amps goes in, 1 amp goes across resistor R1. So the difference, the remainder, 2 amps, goes across the other resistor. Okay, that's one way of calculating it. You could have used the delta V divided by the resistance for resistor 2. You should get the same number. Okay, so there is one example of how you can solve a circuit. And solving a circuit usually means you're given some kind of configuration of resistors, you connect them to a battery, and you want to know the currents and maybe the potential difference across each of the resistors in the circuit. Okay, so there's an example. You might want to look in your textbook on page 473, example 25.3. It's basically the same problem, different numbers. They actually show the resistors connected to a battery in that example. Okay, and they go through the same kind of steps that we went through here. You might find it useful to see it written out in that example. Okay, one difference between here and there is instead of 2 resistors literally beside each other, one of the resistors would be on the other side of the 2 that are in parallel with each other. So it might look slightly different, but in practice it is essentially the same problem, but with just different numbers. Okay, so let's move on. We'll do one more example. 3 resistors in parallel. Okay, so we have an 18 volt battery, and some amount of current is drawn from it, and that will be determined by these the configuration of these three resistors: a 3 ohm, a 6 ohm, a 9 ohm resistor. And now what we have is we have a current I, which goes through this part of the circuit. But as soon as you reach this branch point right there, some current, call it I1, goes across this first resistor. Some amount goes along this branch, and whatever current flows along this branch also gets partitioned into two parts. So we'll call this amount of current which goes through, we'll call that I2. And this current we'll call I3. Now this is a really easy circuit to solve because we have three resistors that are all in parallel. Okay, how do we know they're in parallel? Again, you trace out a path along the wire here, neglecting the internal resistance of the wire. All the points along this part of the circuit, regardless of the branch points, have the same potential. Okay. Likewise, on the bottom, all these points have the same potential that I'm tracing out. Okay. For potential, it doesn't matter if I go across branch points. Okay. It's only for current where that does matter. So the 18 volts across this battery must be the same as 18 volts across each of these three resistors. So the potential difference across resistor R1 is 18 volts. So the current is 18 volts divided by 3 ohms. That's 6. Likewise, the current going across the resistor, I haven't labeled it as R2 in the figure, but it's R2. 18 divided by 6, 3 amps. And finally, in this third branch, for R3 equals 9 ohms. Again, the same potential difference, 18 volts, now divided by R equals 9 ohms, 2 amps. Okay, and the sum of the currents here will be the total current I flowing through this branch that goes through the battery. So if you were asked how much current flows through the battery, it'll be the sum of these three contributions, 6 plus 3 plus 2, okay, which I think is 11 amps. Okay, how much power is absorbed by each resistor? In other words, how much heat energy per unit time is created in each resistor? Okay, well, easy. You can use the expression for power, the V squared divided by R, or you can use I squared times R. You know the current through each resistor. So if you want to know the power, the energy per unit time created as heat in resistor R1, you would use the current I1 that flows through that resistor. Okay, it's not the total current. What matters when you use this equation is it's the voltage across that resistor, or it's the current which flows through that resistor. Okay, so let's see. What about the equivalent resistance? Well, we have a recipe for calculating it. We know all these resistors have the same potential difference across them, therefore they're parallel. Here's the recipe for calculating the equivalent resistance for resistors in parallel. Do the calculation, this is what you get, 1.636 ohms. And the total current will be simply the potential difference of the equivalent circuit. I haven't labeled the equivalent circuit up here, but you can imagine a battery connected to just one resistor instead of these three. Okay, that would be the equivalent circuit. The equivalent resistance is 1.636 ohms. Current is calculated as delta V, the potential difference across that equivalent resistor divided by the equivalent resistance. There it is, 11 amps. We knew that already. And it's consistent, as I said, with the fact that the total current is the sum of these three currents, which is 11 amps.